Hello friends, in this lesson we're going to be talking about a few different ways that we can separate mixtures of different compounds and in some cases even identify those compounds using the differences in their physical properties like their intermolecular forces and whether or not they're polar or the extent to which they're polar. So we'll be talking about two categories of experimental technique and three total techniques today that we can use. The first of which is known as distillation. So distillation separates mixtures by boiling point. Essentially, you are gradually heating up a mixture and the substances kind of boil off one by one in order of increasing boiling point. And if you set this up the right way, they can be collected in separate containers. So this allows you to take a bunch of liquids mixed together and ultimately end up with separate containers that each contain one pure substance. So as you're kind of going through the process of distillation, you're changing out the container that the liquid is being collected into as it goes in order to be able to actually collect these different substances. So we know that boiling point is directly related to the strength of the intermolecular forces. So things with weaker intermolecular forces have lower boiling points. Things with stronger intermolecular forces have higher boiling points. So distillation is really taking advantage of the differences in IMF strengths between the different components of your mixture. If two things have very, very similar boiling points, they're not going to be easily separated by distillation. But as long as you have at least a couple degrees of separation in the boiling points of your different substances, if you're good at distillation and you have the right equipment, you should be able to separate that relatively well. So this is, on the left, is a diagram of what a distillation setup usually looks like. We'll come back to the graph in a minute. So we have some kind of heat source at the bottom. It is depicted here as a Bunsen burner. It is often not fire. Distillation is commonly used for organic mixtures, which tend to be flammable, so you do not want to use fire. But regardless, the picture shows fire. It's fine. It's a basic diagram. That is our heat source. It is heating up our mixture, which is in this round bottom flask. So this is our mixture, our liquids down here, our mixture that we want to separate. Up the top here we have a thermometer that allows us to monitor the temperature. So we know what the temperature is when different substances are boiling and can then kind of use that to figure out which of our containers holds which of our different substances. On the right here, this contraption is what's known as a condenser. It is essentially a double-walled glass tube, so there's like a tube inside another tube, and cold water runs in between them. So the area inside of this is quite cold, is chilled, because what is happening is as our mixture over on the left here heats up, some of it starts to turn into the gas phase, travels up to the top of this setup, and eventually makes its way in here as little gas particles, and then when they are cooled back down by the water flowing outside of that, so the inside here is directly connected to our round bottom flask on the left. The outer part here is filled with cold water flowing through it. That's what these little arrows are, as water comes in here and back out here to keep it nice and cold. And as that is chilled, these are going to condense, hence the name, back into a liquid. And it is angled a little bit downward so that gravity does its thing. And it drips eventually out the end here and into our collection vessel. This liquid coming off is referred to as the distillate. And throughout the experiment, we regularly change out the container that is here. So it's often like a little glass vial is probably the most common unless you're doing a really large volume separation. But we regularly change this out. And by monitoring the temperature and the volume of distillate that's been collected, we'll be able to figure out which of our containers have different substances in them, as we'll see in a minute. So we're heating up our mixture. It is gradually turning into a gas, coming in here and condensing back down as a liquid. And because we are heating it slowly and gradually, at first only the lowest boiling substance is going to be boiling off. As that is finished, the next highest boiling point substance will start to turn to a gas, and then that will be collected, so on and so forth, until we have collected all of our stuff. So if we graph that data I talked about, we should get something that looks a little bit like this. So on the y-axis, we have temperature. On the x-axis, we have the volume of distillate collected. So that's the volume of stuff that has gone through this distillation process. And you should see a pretty stable pattern that your temperature increases for a little while and then it stays constant for a little while. Increases, constant, increases, constant, and that pattern repeats for however many components you have in your mixture. Essentially, whenever your temperature is constant is when you are collecting one pure substance. So that is when your distillate is just one pure compound. So we have that in 3 different places here, which suggests that the mixture that this graph represents contained 3 different components, most likely, or contained at least 3 different components. It could be more if there were multiple that had very similar boiling points, but it definitely can't be less. We have at least 3 different things here. So when the temperature is changing, we have these different sloped parts, particularly the ones in the middle, is when we are collecting a mixture in our distillate. So essentially, it's there and that's there. Essentially, once we've gotten close to boiling off all of this first substance, the last little dregs of it are going to be mixing with the first little bits of the next substance. So as the temperature is changing, you're getting a mix of the lower boiling and higher boiling substances as you have that sort of transition between their temperatures. So as you get better at distillations, these sloped parts get steeper. So if you are either using less than great equipment or haven't done many distillations, you're more likely to see a gradual slope here and you have a larger volume of stuff that is still mixed, which is not usually useful to us. Our goal is to end up with separate pure substances that we can then use for other things. But as you use higher grade equipment, there are multiple different kinds of distillation setups, or just improve your skill, you'll get steeper and steeper slopes so that you essentially have less waste. You have less volume being collected that is mixed. Your temperature essentially goes from from one boiling point very quickly up to the next one with very little distillate collected in between. So when we have changing temperatures, we're getting a mix of stuff. If we have been monitoring our data appropriately, we know that any distillate collected in these regions is going to be not terribly useful to us. We could try again to separate it further if it's something that we really want to collect a lot of, or we can just count that as waste and take what we got of our pure stuff and work with that. So distillation is just separating things according to boiling point, which is essentially in order of increasing intermolecular force strength. Lowest boiling point comes off first, weakest IMFs, highest boiling point, strongest IMFs come off the distillation column last. Our next kind of category of technique is known as chromatography. And there are lots of different types of chromatography, but in the most general sense, chromatography separates mixtures by difference in attraction to two different phases, and we'll talk about what that means in a minute. And we are going to focus on types of chromatography specifically that deal with polarity. There are others, but for the most part, they tend to deal with, or at least most of the common ones tend to deal with polarity. So we have what is going to happen. We're going to talk about two different types of chromatography. In general, they have a lot in common. So we will, in both of them, have our mixture dissolved in what is known as the mobile phase. Which in general can be either a liquid or a gas. We are going to focus on types of chromatography that the mobile phase is liquid. Gas chromatography is kind of its own separate thing. And then that solution is passed through what we call the stationary phase. Which, as its name suggests, is going to be a solid of some kind. So your mixture components that are dissolved in the mobile phase are going to have some amount of intermolecular forces with the mobile phase. As that mobile phase solution is passed through the stationary phase, they will also have some amount of attraction to those stationary phase particles. And they are going to be more attracted to whichever phase is more similar to their own polarity. So differences in molecular polarity are going to create differences in the relative strengths of the intermolecular forces between the mixture components and the mobile phase, and the mixture components and the stationary phase. So if different components in your mixture have different polarities, they will have different relative strengths of their attractions. And what that results in is a difference in how quickly they move through the chromatography system. If something has more attraction to the mobile phase, it's going to stick to those mobile phase particles better, and they are, as their name suggests, mobile, meaning they are passing through the system. So things that are more attracted to the mobile phase move more quickly through that system, through the stationary phase. And things that are more attracted to the stationary phase are sticking more to those stationary molecules, meaning they're not going to move as fast through the system. So there are lots of different kinds of chromatography. We are going to focus on two of them. So the first one is known as thin layer chromatography. Oops. More commonly referred to as TLC. And in this, the stationary phase is most commonly some kind of flat plate packed with powder. Or in a much simpler version, paper. Paper chromatography is essentially the same thing as thin layer chromatography. If you've ever drawn on a piece of paper with a marker and then gotten it wet and watched as the ink bled, was carried along by the water, that's this. That's exactly what we're talking about here, is that that stationary phase, that flat piece of whatever with powder packed on the surface or a piece of paper, has the mobile phase kind of put onto it like ink from a marker. Our mobile phase is just some kind of liquid. It is often a mixture of multiple different liquids, which is not super important, but true. And we let that mobile phase travel up by capillary action. So, I have a diagram down here somewhere. There it is. Beautiful. So this type of chromatography is mostly used for purity analysis, is less used to actually separate your mixtures, and is more used to determine, do I have a mixture or do I have a pure substance? So what we're looking at in this diagram here is essentially a before and after. And in between these two pictures, some amount of time has passed. So the rectangle is our TLC plate, is our stationary phase. The spots that we have down here, oops, are various mixtures or substances that we want to kind of see travel here. So when we're starting out, we're putting our mixtures in different places. So this would be like 3 separate mixtures that we want to compare side by side, so we can see if they share any components, or if they are in fact one pure substance or if they are multiple different substances. And then down the bottom, this little line is supposed to be like the surface of the liquid. That is our mobile phase. So this would be when we have first set that TLC plate into the beaker of the mobile phase and we haven't let any time pass. As time passes, that mobile phase is going to start to move up the plate, is going to start to move up by capillary action. The plate is going to start to absorb that liquid, and that mobile phase is going to carry these mixtures along with it to different extents. So after some amount of time has passed, our mobile phase will have absorbed up to near the top. So this is all wet now. We still have some liquid down the bottom as well, but our plate is all wet. And we can see that our mixtures have separated out. So we started with 3 spots. We now have 3 kind of pairs of spots because these have spread out as they go. So our mobile phase travels up the plate. Do that this way. And it carries those mixtures along with it. Because the different components, so we have like a blue and a yellow spot here, have slightly different polarities, they have slightly different attractions to the mobile phase versus the stationary. The one that moves the farthest is most similar in polarity to the mobile phase. The one that moves the least far is most similar in polarity to the stationary phase. So this allows us to detect that we do in fact have a mixture, that what over here looked like a purple dot is in fact comprised of a red and a blue, and lets us understand something about the relative polarities. Note that I have just phrased this as more similar to mobile and more similar to stationary. Which of those is more or less polar varies. So you can either have a highly polar stationary phase and a low polarity mobile phase, or the reverse. You can have a low polarity stationary phase and a high polarity mobile phase as well. So you have to pay attention to what materials you're using to know whether this means something is more polar or less polar. It just means it's most similar to the mobile phase or most similar to the stationary phase. And last but not least, we have another type of chromatography that is actually used for bulk separation of mixtures, that I want to end up with a container of thing A and a container of thing B. And this is known as column chromatography. So, main differences are really just the physical setup of this thing. Our stationary phase is still solid. It is still a powder. But instead of having it just as a surface on a flat plate, it is packed into a glass tube which is called the column, hence the name. Our mobile phase is still a liquid. Also, mixture of solvents generally. So, mixture of multiple different things, kind of to get the polarity where you need it to be. And in this case, our mobile phase is poured on top of the column. and carried down by gravity. So, third and final diagram here. Again, we kind of have a series of images that are a progression through time. We have our empty, or our column on the left that does not have the mixture in it yet. This is just showing you the stationary phase is packed in here is some kind of granular powder. The mixture to be separated is put in the top. And then each of these represents mobile phase having been poured in the top and stuff starting to travel down. So more and more and more time having passed and more of the solution having passed through the column. So we can see that our three components start to separate, again, due to those differences in attractions to the mobile phase versus stationary phase. The sort of science behind what's happening is exactly the same as it was in TLC. Everything's just traveling in the opposite direction. So the thing that goes the farthest to the fastest is the one that is going to come out the bottom first. And the one that travels the fastest is the one that is most similar in polarity to the mobile phase. The one that travels the slowest is the most similar in polarity to the stationary phase. So same ideas here as with TLC, just kind of flipped upside down, traveling down via gravity instead of up via capillary action. So we can use these differences in polarity to separate mixtures by chromatography, or we can use differences in boiling point to separate mixtures by distillation.